So we're down to the malware analysis stuff. I should mention, by the way, this Saturday, I'm going to start the secure coding class. So it's not for credit, but I'd like to beta test it. I'm going to be doing it all over the place in the summer. And so I got pretty much all of it ready now. All right, so tune into that if you want to. Anyway, as far as malware analysis is concerned, I did not put up the midterm grades for this class yet. I'll get them up pretty soon. I've just been distracted by other things like that secure coding class. But anyway, and I've changed the due dates of the remaining projects because I didn't get to demonstrate anything last week, so my demonstrations are behind. So you'll see all the projects you have an extra week to do them. And all right, so today we're going to talk about Chapter 6, Recognizing C Constructs in Assembly, which is a useful skill to understand assembly language, spotting these clusters work. So here, for example, if I just make code that just prints your hello and a couple of numbers and just compile it, then you can see the simplest thing is how is a function called. All this main program does is call printf with a couple of parameters. And this is something I mentioned before. This is very useful to understand, especially for exploit development. So when you look at it in IDA Pro, if you open this stuff up in IDA Pro, you will not see any of that code. You will see the entry point, public start, and the entry point for a function is some kind of automatically generated Microsoft stuff. It's not getting to any of the code you wrote yet. There's some preliminary stuff that happens first, which is not interesting. So to find the real stuff, you view strings, and then find a string like hello, something it's going to print out, and double-click it, and then you'll end up in the actual code that was written by the developer that does things like print. That's the easiest way I've found to get to the real starting point. That's interesting, the starting point that shows the code that the developer wrote. So then you can disassemble it. You can see it here. So here's the code, but this is useful. Here's the command, print a number 2 and then hello. This is a decimal number and this is a string. So what happens is, this is the function. It pushes the base pointer up on the stack to create a new stack frame. It then moves the base pointer, the stack pointer into the base pointer, so it starts a new stack frame on the first available byte on the stack, and then it pushes arguments onto the stack. This is how it works. It puts on the argument in reverse order. First the hello, then the 2, then the format string, pushes them on the stack. So they're waiting on the stack. Then it calls this subroutine, which is going to be print. That's how it works. It puts these things on the stack. That's what happens when you call a function. And this has interesting, strange effects. One of the obvious ones is if you were not to push arguments in the stack and just call print, then it would print whatever happened to be on the stack. It would assume that stuff was there. It doesn't have any way of verifying this, and that's why you have a format string vulnerability, which we exploit in the exploit development class. Functions do not understand anything that happened in the past. They will just print whatever they have on the stack, assuming you correctly set it up there. And this, I was just writing this up for the secure coding class. This is a fundamental problem. When you assume that the previous routine has done the right thing, and you just use the data assuming it's correctly laid out, that's how you get in trouble, largely, is you make assumptions that the input is trusted, and the input can be made malicious, so you misunderstand it. So global variables are variables available at any function in the program stored outside all functions in some place like the data section. Local variables are the most common ones. They're defined in a function and only used in that function, and they're stored on the stack. They only exist while that function is running. Then that stack frame is freed for reuse. So here, if I look at this code, I define a global variable up here. You define it in C outside any function. So it's globally defined for the whole program, that's G. The local variable here is I equals 3. So then I print G and I here. I'm going to print the number, the global variable and the local variable, and you'll see them here. So here it's it's pushing the format string on there. It's going to put them in reverse order, so it's going to be the local variable first. The local variable just has this address, which is on the stack, 41B100. The global variable has, wait, here it is. Here's the Local variable has this relative to the base pointer address. That's in the current stack frame. Base pointer plus an offset. That's a local variable. The global variable has a fixed address here, which is pointing to another section, like the data section. And then it pushes an offset to this. So that's how you can tell them apart. Local variables have an address on the stack frame, so they'll be related to ESP or EBP. Global variables just have absolute addresses because they're pointing to different segments. So you can tell them apart. So now you consider arithmetic operations. Here I'm going to define some numbers, and then I'm going to add, subtract, multiply, and divide those numbers, and then print them all out. And so when you print them out, you can see this is a local variable. Put a 3. That's going to be I is E base pointer plus 8. EBP plus 4 is going to be J. That's 6. So then I move, let K equals I plus J. So I define this variable K to just be EAX must be pointing to that. You take 8. Oh, no, I did it this way. First you put one variable at EAX, then you add another variable at EAX, then you take EAX and put it here. So these 3 assembly language instructions together do this. This is often the case that you do not have one assembly language instruction that will do what you need. You have to combine multiple instructions, especially in ARM, you almost always have to. And so here we are. I'm moving to ECX, this number in ECX, and then move this. And I'm not quite, oh, subtract. This is how you did the subtract. Move one in here, then subtract the other in ECX, then take ECX and put it on the stack. So those 3 commands are this one, L equals J minus I. Then down here, I'm going to take a number and put it in EDX. I'm going to multiply it by this number, and then I'm going to move the result into this address. So that is this one. M is J times I. And then I'm going to do floating mathematics. You notice this XMM, these are the floating point registers. I've almost never used them, but there are special floating point registers for that kind of mathematics that you use. So there you see what arithmetic operations look like in assembly code. All right. And let me see a comment there. Let me see if there's, that starts in China. All right. Anyway, so that's, all right. Let's see if I can get back to my slides. So then there's if. So here I'm going to have I is 3. If I is greater than 0, print something, otherwise print something else. So this if construction is real important. That's a branch. And here's what it looks like in assembler. Up here, I have this code which prepares it. It sets a variable to 3, and then it does a compare with 0, and then jump less than or equal to 0. So if it's less than or equal to 0, it will jump down here and say it is not positive. That's right. And if it is greater than 0, we'll go here and say it's positive. The red, so that's what this does. That's what it looks like. There's going to be a compare and then a jump 0, jump not 0, jump less than 0, jump greater than 0, that sort of thing. And that's what a branch looks like. All right. And for loops. Here's a construction that will do something 100 times. It starts with I0. It sees if I is less than 100, and if that is true, then it executes this, which increments it. So next time it will be 1 and 2 and 3, so it'll go from 0 to 99, and it will print this number 100 times. So that's what goes on here. That's what a loop looks like in C. And here's what it looks like in assembly code. It takes quite a few statements. Here, you define the variable locally, I, which is going to be E base pointer plus variable 4. You put in a 0. Then it's going to do a jump down here to 16. There it's going to compare the number to 64 hex, which is 100. If it is greater than or equal to that, then it's going to jump down to 40102F, which is off the page, which is going to exit this loop. Otherwise, it's going to go here. It's going to move the variable into ECX, push it on the stack, print it, call printf, then jump back to here, and now it's going to, here's where it increments the thing. It puts the variable in EAX, it adds it, and then puts it back in the location. So these 3 commands increment that variable. So this is the I++. So you can read it. It's a little hard to read, but this whole thing is that little loop in C. I see another comment in the chat. The robot nearly fought back. Yeah. It doesn't look like it actually attacked a human. That's true. All right, so then there's an array. You can define an array that can hold 5 values with these curly braces, and here's the values. And And then they're all integers, so they are, I thought they would be 8-bit integers, but I see a 978. I guess it must be 16-bit integers. I'm not quite sure. It depends on the default for C. So now you define a local integer and a 5-array local here, and then you copy them. So this is going to assign data to the local variable, and this is going to assign data to the global variable. So we should be able to see all that in that loop. So the interesting part here is the array. So to you initially put 0 in this location, then you jump down to 8 here, and now you compare it to 5. This is the loop going from 0, but not more than 5. If it's greater than equal, then you jump out of here and you're done. Otherwise, you assign values to the element B. This is going to put a variable 18 here in E, C, and D, and then it's going to move D into this location. This is what it looks like to fill an array. You're going to take a base pointer plus an offset to get you to the start of the array, plus 4 times ECX, which is a counter, because every value is 32 bits long, so it is 4 bytes. So you're going to increment this, ECX. The first value goes in the first 4 bytes, the next value goes in the next 4 bytes, and that's how you fill an array. And so this will assign it to that element in A. So this is going on the stack, and this is going to an absolute address relative to that in another data segment. So this is the global variable, and this is the local variable filling the array. And then there's a for loop going on with all this. It will do it 5 times. All right, let me take a look for comments. Okay, nothing. All right, so here's the summary of what we've done. You find the code. The way I've learned to find code, I've never read a book that told me how, is to use strings, find a string it prints, then use the cross-reference to that to find the code that actually handles the strings. That will get you to the code that the developer wrote. Otherwise, you have to wander through a bunch of Microsoft-written code, which is boring. Function calls, you push the arguments onto the stack in reverse order, and then call the function, which will just assume that whatever it finds on the stack is what it should be using. For variables, you can have global variables in a different segment in memory and available to all functions, and local variables are on the stack, only available to one function. If you do arithmetic, you typically move the variables into registers, you do the arithmetic on the register and move the result back into the variables. And for branching, you do a compare with compare or test, then a conditional jump, and then the red arrow in IDA Pro shows if this condition is false, and the green arrow if it's true. That's what it looks like. So let's try a Kahoot about this stuff. I should have it ready to go here. There it is. All right. There's 10 people online. Hopefully there's some people that want to play the Kahoot. Oh, good. Good. Enough to actually make a competition of sorts. I'll wait a few more seconds. I'm not generally compared to Gates anymore. Gates is retired. Not in the business anymore. All right. so what variables are on the stack? Yep, those are the local variables on the stack. They only exist while you're executing one function, and when you return, that memory is released to be reused for other purposes, and those values are gone. All right, so what C construct looks like 3 boxes connected by arrows, like that there. That's an if. It has a condition, and if it's true, it goes one way, and if it's false, it goes the other way. All right, what construct appears as several push commands followed by a call? That is a function invocation. You push the arguments on the stack, and then you call the function. All right, so what construct looks like this? D word followed by an address. That's a global variable. And by the way, you can notice that here. Remember, Microsoft Code always thinks it's running at 400,000, and the text section always starts at 401,000. So this is pointing to a different data segment, not a text segment. This is not. So you can tell from the way this is laid out, it's pointing to something like the data or the R data segment, one of those other segments that are higher up in memory. That's a global variable.